Newton's law of cooling. There he is, Isaac Newton. Surely we are familiar with the idea that objects cool down or warm up to match the temperature of their surroundings. Basic law of thermodynamics. Things that are in the same environment cool all to the same temperature unless they have their own internal heat or something like that. Like obviously it doesn't happen to humans. You don't become the surrounding temperature because you have your own internal heat. In fact, the rate at which the object's temperature is changing at any given time is approximately proportional to the difference between the temperature and the surrounding temperature. Okay, long sentence that means this. After you cook a potato, I don't know if you ever tried to eat a baked potato right after it comes out of the oven. It's a nightmare. It's really, really hot. Yeah, like it'll burn your mouth good. But if you open it up, it doesn't take long before you can eat it. Like it feels like a long time when you're hungry, but it's pretty quick. Yeah. But if you go back to the potatoes that were cooked that people didn't eat, an hour later they'll still be warm. Yeah. So when your temperature is very different from that of the surroundings, you cool off very quick. You lose those first few degrees pretty quick. But actually to get down to room temperature takes a long time. Okay? And that's what they're saying there is how far you are away from the surrounding temperature decides how fast you're going to lose heat. Well, that's exactly what we've been talking about. More temperature means more temperature loss here. A potato that's 100 degrees, say it loses 2 degrees a minute. By the time it gets down to 30 degrees, it's maybe only using 0.15 degrees a minute. It loses its speed there. So if T is the temperature of an object at time T, and T at S, okay, that's the important thing is, this is the time. This is the temperature, and this TS is the temperature of the surroundings. So it really depends on what you're in. The temperature of the surroundings, if you put your baked potato on the counter, the temperature of the surroundings might be 20 degrees Celsius. You know, the temperature of the room. You drop it in a bucket of ice, which is 0, well, that's different. So that's what's incorporated here is the temperature of the surroundings, where you put your potato, basically. Since T at S is constant, we also have that the derivative of temperature is just d by dt of T minus Ts, and we get this beautiful equation a couple of lines later. Newton's law of cooling, which is the difference between your temperature and the temperature of your surroundings is equal to the T naught minus Ts, where T naught is where the temperature you started out as. And now I am full aware when I throw something up on the screen like that, like I have no idea what any of these symbols mean. The example really brings it home, is to bring home what exactly is going on there. And this development is a very simple development where you come up with the rate of change of temperature with respect to time 2 different ways. One way is it's proportional to the difference between your temperature and the temperature of surroundings. And the other way is to say, hey, if I just take the derivative of temperature, I get T minus Ts. All that is fine. You can look back at that. But this is a lovely equation on what it can accomplish. So I want to go right into showing what this equation does with 2 examples. Because that's what you really need, is how to use this thing. And basically, to use this thing, you got to know what each of these little pieces are. So let me write them all at one time so you can see what you have to sub in here. Ts is the temperature of the surroundings. And this is the part I was talking about, that it matters whether your potato is sitting on the counter or dropped in a bucket of ice. T naught initial temperature of the object And the K needs to be found for whatever object you're talking about. That is, potatoes take a long time to cool off, but tinfoil does not. I don't know if you notice when you cook with tinfoil, you can touch the tinfoil right after it comes out of the oven. It cools almost instantly. Yeah, so the K is based on whatever object you're talking about. So that we got some information here about a hard-boiled egg. It's at 98 degrees Celsius, and it's put in a pan under 18 degrees Celsius water to cool. After 5 minutes, we know the egg's temperature. How much longer will it take to reach 20 degrees Celsius? Now, I can tell you a lot of exponential questions are like this, where there's two parts. Part one, get this K value. I mentioned that in a previous example. Go after the K value first. That's usually your first move, is to get the K value, because then you'll have a much better equation to deal with. So I'm going to sub in everything I know. I do know the temperature after 5 minutes. So when T equals 5, T equals 38. But other things I have is that T naught was 98. And temperature of the surroundings was 18. So there's a whole bunch of subbing that has to happen in here. And when you've got an equation like this that's got a lot of stuff in it, that's what's going to happen, is you're going to have a lot of subbing. Let's see if I've got enough stuff. 38 minus the temperature of the surroundings is 18 equals T naught, which was 98, minus the temperature of the surroundings, which is 18. E to the negative, I'm going to sub in that K, e to the negative 5K. And again, that's that pizza step where you go, as much as this question asked, as many variables as it had in the question, as many constants and variables that I had to sub in, it gave them all to me. So I can sub them all in there, and then you look at it and go, oh, well, I can get this K value now. That's in exponential equations, that's usually the first step. So let me just tidy this up a little bit. 20 equals 80, e to the negative 5K. 0.25 equals e to the negative 5K. Ln 0.25 equals negative 5K. And then I get ln 0.25 over negative 5. There's my K value. Now, I want to mention that if you're really doing these questions, you might leave that as it is, or you might go with a decimal. Math people, we want to do better with ln. I want to just experiment with ln a little bit to make sure you can see that we often can do a little better and tidy up ln. See, ln 0.25 is ln a quarter. And then that's ln of 4 to the negative 1, which I can bring out front, and I can really tidy up this ln and end up with ln 4 over 5, which is a lot nicer to carry around than the previous K value I had. It's the same thing. You get the same answers. But in math, sometimes we want to really tidy these things up. So now, once I have my K value, I'm ready to go. I can write this equation. Temperature minus, what was the temperature of the surroundings again? 18 degree water equals T naught minus Ts. That's always 80. And then e to the negative ln 4 over 5 T. Now that's a good equation. And I'll just let you stare at it for a second to make sure you agree that that's a really good equation. And you'll see what I mean by that in a second. Did I make a mistake? 98 minus temperature of the surroundings. Temperature of the surroundings is 18. Oh, that looks right. Mr. Yakimish, what's happening? Why is that such a good equation? What is it about everything that's falling apart there that, you know, the rest of this is blah, 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 but what is it now that makes it a great equation to do problems? If you know time, you can get temperature. If you know temperature, you can get time. Like that now is a complete equation. It didn't have all this other stuff in it. The work I did to get the K paid off with a nice equation. Because now I can use this as how much longer will it take to reach 20 degrees Celsius. So I'm just putting the 20 in over here. And then you can order a pizza because you know the rest of it is just work, just that algebraic work we saw in part 1 of this lesson. Yeah. So here I go. 2 over 80 equals e to the negative ln 4 over 5. Ln both sides. I get ln of 1 over 40. I'm doing some extra steps along the way. I hope these steps don't cause you too much trouble. Ln 4 over 5t, and so I get 5 ln of 1 over 40 over negative ln 4 equals t. I did that all at once. Let me just make sure I did that right. 1 over 40, yeah. Move the ln over. That's just this part here, yeah. Negative ln 4 over 5t, yep. 5 ln 1 over 40, yeah, that's right. Over negative ln 40, yeah, looks great. Now I'm ready for my calculator. Finally, after all that. Which again, for chemistry type people, you might look at that and go, well, couldn't I have gone to decimals way earlier in this? If you were just going to go to decimals in the end anyways, couldn't I have gone to decimals a lot earlier? And the answer is, well, yeah, actually. You know, like if you don't mind carrying those things around, but I'm trying to keep the math alive in all this. Let me type this in and see what I get. 5 ln 1 over 40 bracket divided by negative ln 4. 13.3. Did I answer the question? Did I answer the question? I don't think I did. Who's with me with the problem here? Therefore, it will take 13.3 isn't the answer. What's the answer? 8.3. They tried to be tricky there. He said, after 5 minutes, the egg was down to 38 degrees. How many more minutes? And my t that I've got here is from the beginning, so it's 8. I'm not setting you up. I don't like questions like this. Well, if I ever put something like that, I usually used to my test, I usually put that in bold or italicized or something like that. I'm not trying to be tricky, really. You know, they wanted to know how much more time. Any questions there? I'll give you Newton's law of cooling on the test. This isn't about memorizing Newton's law of cooling. You have to know what the parameters are, but I'll just write that on the board, okay? We're not here to memorize Newton's law of cooling. Certainly not. It's just one of the many applications of what we've been studying here. One more example and then I'm done. More time? More time here? Emmett. Yeah, it works exactly the same way. Yeah? So, I mean, it's good for knowing how long it takes for the beer to be cold. Definitely works well for that. But also, when you put something in the oven and want to warm it up, it covers that as well. And if the equations were just for that, it would be cute. But it's for any temperature transfer that goes on out there. Between any two objects, and one of the upper year course in university is called thermodynamics, and it takes this a step farther and goes, how does heat really transfer between things? Because now, and I don't know how far you've gotten chemistry and thermodynamics, you pretty much ignore heat transfer in the middle of, you say, oh well, delta H is whatever, and you pretty much just leave it on the shelf because the math isn't ready yet, you know. But now with this, we can deal with whatever heat transfer is going to happen between an object and its surroundings. Yeah. Is that what you meant? Other questions? Last one. It's sometimes actually easier to work with when they give you a whole table of values. Now the difference between this question and the previous one is the egg with one piece of data, that is after 5 minutes the temperature is found to be 38 degrees, you really don't have much information about the egg. We take this and we go, oh yeah, 13.3 minutes. With one piece of information about the egg, with a temperature gauge that's suspect, every temperature gauge is suspect, you know, you don't really always have that good information. So if we can incorporate a lot of information about something that's cooling, we can get a better equation, All right, and that's the point of this question, is to go, if we had a lot of information about the coffee cooling, we could collect a lot more information. Now, what's hard about this is you can't just sub in one single value when you've got a lot of values to use. Because the question is, which of these values would you use? Yeah? Because any one of them could be the one that is not a very accurate number. You know, we want to follow the trend. So what I did was, instead of using the whole equation, see over here it was t minus ts. Instead of using the whole equation and subbing in and finding the k values and all that kind of stuff, I just took the data, and you can do this in your calculator too, and I went in and I put it into the calculator. And you can do this in a minute if you want, but don't necessarily get distracted by that, because what you want to know is, can the calculator do this? So I put all the data from the table in my calculator, you know, to 60.3. See, I'm finding the equation for t minus ts. That's why I'm using the t minus ts column. I'm getting an equation for t minus ts. And then I put in, okay, at 2, it's 60.3. At 5, it's 44.5. All the way down, I put all that data in, and your calculator's wonderful at this. Then you hit regression. We did this now. Now this is going back, yeah? We were regression kings and queens. Back in September, we did a lot of regression type things. So I'm just doing a quick version of it here. You type the data in and you hit regression. There's lots of choices for what kind of regression we'd like to do. We'd like to do an exponential regression, and it gives me a nice equation just like that. So when you have lots of data, get a computer involved and you can really match the data nicely. So what I get here is, I used E as the base. You don't have to use E as the base. You could use another base. So I'm going to go back and say, okay, do exponential. Oh, my calculator only lets me do E. Your calculator, you've got another choice there. You could use A, B to the X, and it'll get the best base it thinks available. But mine uses E, so it doesn't really matter. So A, 61.65. Excuse me. E to the, what B did it use? Negative 0.75. Oh, that's a T. The calculator said X. Of course, I know it's T for time. And this has matched the data as well as possible. It said, you know what, your temperature might have been thrown off, your measurements might not have been that great on a particular one, or the coffee got stirred a little bit, or whatever happened, you know? But this is the best possible match for T minus TS. Then I can do the rest. I know the temperature of the surroundings is 4.5. They told me that. And what's the question? Estimate the time. Hang on. Ask the really good question here, Mr. Todd. The really good question is, why is this such a good equation? I know it's complicated. T minus 4.5, 61.65, e to the negative 0.75 t. But what is it about the variables that are in the question that tells us if it's a good equation to use? Time and temperature. That's all that's really going on here. Plug in one, get the other. You know? And then it said, estimate when the thermometer will read 8 degrees. So I'm doing 8 minus 4.5 equals 61.65 e to the negative 0.075 t, and the rest is history, right? Your algebra takes over and finishes off the rest of it. Let me do that algebra and then check it. 3.5 equals 61.65 e to the negative 0.075 t. 3.5 over 61.65 equals e to the negative 0.075 t. As you get better at these, you start to skip steps as you know what's going to happen next, because they're very, very repetitive. Equals negative 0.075 t, and then ln 3 over 61.65 over negative 0.075 equals t. Let me type that all in and see if I get a number that I can live with, and then I'll check it all out with my notes there. What do I got here? Ln 3 over 61.65. Oh, 3.5. Yeah? I hear some rumblings out there. Is that the way you're talking about? I just randomly dropped the 0.5 there for no really good reason. Divided by negative 0.075. How did I do? Good. 38.5 0.2 equals T. Let's look at my table and see if it's somewhat reasonable. I'm trying to get down to temperature 8 degrees, or T minus TS is 8. So this has got T minus TS to get down to 3.5 degrees. I'm looking for 8 in this column here. 38 minutes looks plausible. You really want to check those because it's easy to drop a negative or a ln or a 3.5 and totally mess this up. So you really want to look that over and make sure that it makes sense. Question? Oh yeah, great move would be able to just go, couldn't I just then take the calculator, get it to graph this thing, and then sub in, also draw the line, y equals 8, do the intersection on the screen? Yeah, great stuff, for sure. I'm showing the algebraic method, but once you've already got all that data into your calculator, you could switch over and graph those points with the curve, draw a line y equals 8, and then you could get the calculator to get that exact number here instead of doing all this work here. Yeah, possible. Yeah, very good. Play with your calculator, see if you can get it to do it. Yeah. Other questions there? Lesson, when you've got the data, use it. Don't rely on one point. When you've only got 1 point, you just got to sub in, you got to go, oh, this is the best we can do. When you got the data, it doesn't take long. You punch this in your calculator, you hit regression, boom, got the equation, as opposed to building the equation myself.